Welcome. 3.3.1 Rules for Differentiation. Finding shortcuts. This is one of my favorite lessons of the year. This is where kids kind of really start to cheer because we learn how to do problems like this super fast. So if I gave you y equals x to the fourth plus 3x squared, and I said find y prime, right now you'd probably grown big time because you'd have to use that limit function, right? You'd have to do the limit as h approaches 0 of f of x plus h minus f of x all over h, which would be the limit as h approaches 0 of x plus h to the fourth plus 3x plus h squared minus that whole x to the fourth plus 3x squared all over h, right? Plugging x plus h in, plugging just an x in, subtracting them, putting them over h. You're probably looking at this like, oh no, I got to take the fourth power of that one. It would take forever. However, once we learn our shortcuts, we can answer this in about 2 seconds. Like literally, it's super fast. So that's kind of cool. So let's start with our first shortcut, the derivative of a constant. So if I gave you something like f of x equals 3, and I said f prime, find f prime of x. If it's just a constant like 3 or 8 or 92, a constant is just a number that's never changing. It'll always be a horizontal line when you graph it, right? Well, what's the slope of a horizontal line? 0. So the derivative of a constant is always, always, always 0. If you don't remember, d dx again stands for derivative. So if I'm just asking for the derivative of a constant, the derivative is always 0. In this lesson, I'll try to mix up this notation with that notation on occasion just to get us used to the fact that it means the exact same thing. All right, so here's our example. Y is equal to 28. What's y prime? Well, 28 is just a constant, so y prime is 0. All there is to it. All right. All right, but what if the function is a little bit more complicated, like this, right? What if I had to find the derivative of that? For this, we're going to find out that rule on our own. I've got a bunch of f of x's here and a bunch of the derivatives, f prime of x is there. Take a look at that and see if you can find some pattern that always seems to happen. All right. X to the fifth becomes 5x to the fourth. Take a look at that 5. 5 came down, and then that 5 dropped down to a 4. Same thing here. That's a 5, dropped down to a 4. 5 comes down, 5 times 4 is 20. 3 comes down, 3 times 2 is 6. Drop that 3 down to a 2. So every time that power just kind of seems to multiply times the front and then subtract 1 from the power. 2 minus 1, that's x to the 1, right? Here's x to the 1. 1 times 11 is 11. Technically, this would be x to the 0, but anything to the 0 power is 1, right? So that's just 11. Watch out for negatives, right? Negative 2 times 4 is negative 8. But when I drop negative 2 by 1, when I subtract 1 from that, it doesn't become negative 1, it becomes negative 3. So if you do this, if you did the derivative long enough, especially that long version, you would end up catching that this seems to always happen. In fact, we can prove that it always happens. But I'm not going to waste your time going through that proof. So I'm just going to pop this up here, power rule. So power rule says if you're taking the derivative of x to some constant, to some power n, the n comes down right there, and then you subtract 1 from that power. So I've got an example down there, 5x to the cubed. What's the derivative of that? Well, 3 comes down, 3 times 5 is 15. And now instead of x to the third, x to the second. You might recall when we've been doing the derivatives in the past, every time we did the derivative of something that looked like this, a parabola, it always seemed like the derivative was going to be a line. Well, that's because anytime you've got something to the x squared, the 2 is going to come down and it's going to be like, let's say ax squared. That's going to be 2a times x to the 1, which is just the equation of a line. So super nice, super fast. Some practice. I would recommend you pause the video, try these on your own. This is going to be huge that you can do these problems. They shouldn't be hard. The last one might throw you for a little bit of a loop, but it's not too bad if you remember your rules for radical signs. All right, I'm going to go over these. 2x to the 4th. That's just 8x to the 3rd, right? 2 times 4 is 8. Drop the 4 by 1, 2x to the 3rd. This one, negative 3 times 5 is negative 15. Subtracting 1 from that exponent, watch out for that, would be x to the negative 4. And then this one gets some people until they remember that square roots we can write as a exponent. I can rewrite this as the derivative of x to the 1/2, because x to the 1/2 and square root of x are the exact same thing. And then they're like, all right, so bring the 1/2 down. That'd be 1/2 x. Subtracting 1 from that exponent, 1/2 minus 1 is negative 1/2. All right. Sum and difference rule. This looks complicated. It's really not. It's just saying if you're taking the derivative of a sum or a difference, it's the same thing as finding those derivatives separately and adding or subtracting them. So a real quick example. If I asked you to find the derivative of this whole thing, you don't have to do anything special. You can take just the derivative of each of those individual terms separately. So this derivative is going to be, derivative of that is 15x squared minus 16x, because x to the 1 is just x, plus derivative of that is going to be 3, right? Because it was 3x to the 1. 1 comes down as 1 times 3 is 3. Be x to the 0, but x to the 0 is the same as 1, so that's just 3. And then a lot of times I see people trying to put plus 7 there, but don't forget it's not a plus 7. It's gone. It's plus 0. Plus 0 because that's a constant, and the derivative of a constant is 0. Some people like to remember it like this. They have to say 7. Well, 7 is the same thing as 7x to the 0, right? No difference again. So if that 0 comes down, 0 times 7 is 0. So derivative of a constant is 0. So that part goes away. Obviously, I could simplify this. 15x squared minus 16x plus 3. Typically, when people answer this problem, they just give that answer. They don't bother writing the 0 there. For your notes, it might be a nice thing to write 0 there, just to remind yourself that the derivative of a constant is 0. I've been teaching this for a few years. That seems to be the one that people forget. For whatever reason, they see a 7 and they just say, well, that stays there. It doesn't. Derivative of a constant is 0. All right. Those are essentially our derivative shortcuts. They're huge. Here's an example problem, which we might as well go through. It wouldn't be too bad. This one's asking, find where the tangents of this thing are horizontal. That shouldn't be too bad. We know when tangents are horizontal, they have a slope of 0. So all I really want to find out is when this equation has a slope of 0. Well, to find slope, we need the derivative, because derivative tells us slope. So I got to find y prime. Y prime would be 3x squared minus 8x minus 3. I really care when that derivative is 0, because I'm looking for when the slopes are horizontal, when the slopes are 0. So set that equal to 0. 0 equals 3x squared minus 8x minus 3. I just need to find where that happens. Remember with this, if you wanted to find where a quadratic, like anything to the x squared power is 0, there's a few ways to do it. Fastest way, factoring, if it's factorable. If you can't factor it, then you might need the quadratic formula. Let's find out with this one. That'd be 0 equals, all right, that's a 3x squared. So this is going to have to be a 3x and an x. That's a 3, so one of them is going to have to be a 3. I could put the 3 here, but I think it's actually better to put the 3 there and a 1 there, because 1 times 3 is 3. The reason why is these 2 times each other is 9x. Those 2 times each other is 1x. 9x and 1x can get to negative 8x as long as the 9x was negative and the 1x was positive. This one is factorable. Oops, lost some of my work. All right, which means since 0 is equal to that times that, one of those has to be equal to 0. If this one was 0, x would be a negative 1/3. If this one was 0, x would be 3. Those are the two locations where you're going to have a horizontal tangent, at negative 1/3 and at 3. It shouldn't surprise us too much that it has two horizontal tangents because this is an x cubed function, right? X cubed functions typically look something like that. So it's going to have a horizontal tangent once and twice. This particular one happens to have one at a negative 1/3 and at 3. That's not a very good drawn to scale, but should make sense. All right, one last thing to learn today, and it's actually pretty easy. It's just going to be new. Normally I have this part covered up, but I don't this time. It'll be all right. All right, find f prime of x. We know f prime of x is just the derivative. Oops, I forgot to name this. I should have named that f of x. There we go. Now we know f prime is the derivative of that top one. It might be a good idea to try to find this derivative on your own. Maybe pause the video and try to find it on your own. But I'll do it right now. Okay, so this derivative is going to be 4x to the third plus 6x squared minus 6x plus 4. All right, here we're going to learn some new notations. F prime was just the derivative of f. What do you think f double prime is going to be? If you guessed the derivative of the derivative, you're right. We actually have a name for that. It's called the second derivative. It's just the derivative again. So find the derivative of the derivative. And that shouldn't be bad. Give it a try. This would be 12x squared plus 12x minus 6. Guess what f triple prime is? The third derivative. The derivative of the derivative of the derivative. You're just asking to find the derivative again. This will be 24x plus 12. After 3 primes, after 3 of those marks, it gets pretty bad to try to keep going to 4 and 5 and 6 and 7 if you wanted to find the 4th, 5th, 6th, or 7th derivative. So after that, the notation just changes to a number. The 4th derivative would be 24. If we wanted to keep going, we could, but here it's going to start getting boring. The 5th derivative of a constant is 0. The 6th derivative, well, 0 is still a constant, so the derivative of that constant would be 0. The 7th derivative, the 8th derivative, the 9th derivative is just going to continue to be 0. These are called higher order derivatives, right? That's a first order, second order, third order. These are higher order derivatives. They actually have a really good implication in some real life examples. It helps us to find things like acceleration and something called jerk, which is kind of cool. We're going to talk about those in the future, actually not too long from here. But for now, just let's practice getting used to that notation. Being that just means the second derivative, find the derivative twice. Find the derivative and then the derivative of the derivative, and then get used to that. You might remember that there was a couple of ways to show f prime, right? I could show it like that, or I could show it as df dx, right? So there is an equivalent derivative notation for the second derivative and the third derivative and the fourth derivative. That's on the next page. Probably be worth your time to write it down. Spend a little bit of time kind of memorizing what it looks like so you get used to it. All right, so here's the notation. This one we should have already known. If we have y prime, that's the same as dy dx. Second derivative is the same thing, except it's with like a little power, d squared y dx squared. So notice where those exponents go. They're not both at the end. It's in the middle of the numerator for the d, at the end for the x squared, which is kind of weird. I can explain that later. I'm not going to waste time in this video right now because I really want you to get to practicing some of this stuff while it's fresh in your memory. Practicing it while it's fresh in your memory can really help cement this knowledge so that you can kind of get it in that memory quick. Third derivative, same thing. Nth derivative, same thing. All right. Here is your assignment, section 3.3.1. bunches of problems just to practice it. Once, well, there's not that many actually. I wish there were more. I should make more. Maybe I'll make a worksheet for this. At this point, I haven't made a worksheet for this, so just do those ones. We're gonna do this forever from here on out, so I'm not too worried. You'll catch on pretty quick. But do those problems. Maybe I'll come up with a worksheet to do it, or a little extra practice, but I think we'll be okay. That's it. I'll see you guys tomorrow.